Hey guys, today we're going to be talking about limits. Again, we've talked about limits at the beginning of the year. We're going to revisit them having calculus in mind. All right, so let's just talk about what a limit was. So remember that a limit is the value that f of x or the y value approaches, right? That's the key word, approaches, as x approaches a number c. So for example, take a look at this graph down here, right? This is a graph of a linear equation. And if you look at the bottom here, this is the x value c, right? So it could be x equals 5, x equals 3, and so on. The limit is this. As somebody is approaching c from the left-hand side and they look up at the graph, right? So if the person is here and they look up at the graph, this is the y value. You get a little bit closer to c, you look up at the graph, this is the y value. So do you see that the y value is going down? It's decreasing. Well, as you get very, very close to c, you'll see that it's going to approach this y value right here. All right, so what happens from the left-hand side? What happens if you approach c from the left-hand side? So if you're at this point here, you look up, here's the y value. Move a little closer, the y value has moved up. Move a little closer, the y value has moved up, right? And then you can tell that it's going to be approaching this value L eventually, right? So the value, y value, which the graph is approaching is the limit, okay? All right, so let's take a look at this example here. It says to estimate the limit of 4x plus 1 as x approaches -1 using a graph. And then it says to use a table of values to support the conjecture. Well, you know what I'm going to do? I'm going to do this in the opposite way. I'm going to do the table of values first and first come up with a conjecture. So let's take a look at the y values here. The limit is asking us, it's asking us to find the limit as x approaches -1. So I've made a table here. This is -1. And if you see here, I have values as I go down here that are approaching -1. So -1.01, -1.001, and then finally it approaches -1, right? And then on this side, I have -0.9, -0.999. Eventually, I'm getting very, very close to -1. Okay, so in the first case, I plug -1.01 into that equation here, and I get -3.04, okay? Next, I plug in -1.001 and I get -3.004. So as I move this way, what y value do you predict this is approaching? I think you're all thinking -3. Well, now let's go from the other side. If I plug in -0.9, I get -2.6. If I plug in -0.999, I get -2.996. So as my x values get closer to -1, what y value are my values approaching? Well, -3. So do you see how from the left and from the right, I'm kind of zeroing in on -3, right? That's the idea of a limit. And now let's graph this function here, and let's see if the graph and the table support one another. So 4x plus 1, this is the y-intercept, plus 1. I go up 4 over 1. That's what that looks. And here we're going to go down 4 over 1, so like that. Okay? All right, so take a look. As you approach -1 from this side, where is your y value going? Oh, look. Down to -3, right? And as you approach -1 from this side, where is your y value going? Oh, look, up to -3. So the limit of 4x plus 1 as x approaches -1 is in fact -3. All right? Okay, let's move on. All right, so there are 3 situations, there are 3 cases that we might come across, right? One case is this, that the limit as x approaches c of a function is some number, but the value at that point doesn't exist. So for example, take a look here. This is the value of c. As I approach c, right, my y value is approaching this number L. As I approach c from here, my y value is approaching that same number L, right? Did I actually talk about, getting to that point? No, I'm just talking about approaching that point, okay? But now take a look. What is f of c? What is the actual value at c? Well, there's a hole there. It's undefined, right? So even though there is a limit, the value at that point is undefined. Okay. Here, as x approaches c, from the left-hand side, the y value is approaching L. As x approaches c from the right-hand side, the y value is approaching L. So the limit is equal to L. But what is the actual value of the function itself? Well, there's a hole right here, but there's a point here at n. So the actual value is n. Okay? And then take a look here. As x approaches c, y value approaches L. As x approaches c, y value approaches L. So the limit is L. And the actual value of the function is also L, right? So there are 3 possibilities here. The point is that the limit, it's possible for the limit to exist, but for the actual value of the function to either be something else or not exist at all. Okay? All right. So next one here, let's take a look at the graph here. And it says the limit as x approaches 4 of x squared minus 16 over x minus 4. Okay, so you should remember from Algebra 2 or from Algebra 1 that if you have a denominator with a variable, there is a possibility that the function does not exist there, right? So let's take a look at this function. The limit as x approaches 4, x squared minus 16 over x minus 4. What would happen if x was equal to 4? Well, I would have something divided by 0, right? And this function would be undefined, right? That means at x equal to 4, there is a discontinuity. This function does not exist, right? All right, we're going to talk more about this, but for now, why don't we use our calculators to see what this looks like? Right, so here's the graph, here's the function right here, right? And when I graph it, this is how it looks. I'm just going to adjust my windows to see a better picture here. Window settings. I'm going to move Y max to about 10, and I'll tell you why, right? So here we go. So look, at first glance, there doesn't seem to be any discontinuities here. None of that scary stuff I was talking about, dividing by 0 and this and that, right? But wait, what happens as you approach 4, right? If you trace, right, what happens as you approach 4? So take a look. As I'm approaching 4, look at the x values. X equals 3, y equals 7, and then 3.3, y equals 7.3, 7.6, right? It looks like I'm getting closer and closer to 8 here, right? 3.9, I'm at 7.9. And then look, 4.2, I'm at 8.2. Okay, so what happened at 4 then? So in trace mode, if I type in 4, look, it is undefined. Okay, so let's take a look here. Let's just reproduce that graph here. That's how that looks. So what happens as x was approaching 4, right? We were nearing y equals 8, right? Right here, just like that. But what happened right at that point? There was a discontinuity. It's because there is a little hole there. Okay, but from this side, my y values were approaching 8. From this side, if I move my cursor down, my y values are approaching 8. And because from the left and the right, the limits are approaching 8, I can say the limit of x squared minus 16 over x minus 4 as x approaches 4 is 8. Okay, now let's try it with the table of values. Here is my number 4, right? As I move closer to 4 at 3.99, my y value is 7.99. Here, my y value is 7.999. And if I move closer here at 4.01, the y value is 8.01. Here, 8.001. So take a look. Because from both sides, the y values are approaching 8, I say the limit is equal to 8. Now, so notice this had nothing to do with the fact that there is actually a hole at that point, right? Because a limit doesn't talk about what happens at the actual point. It's just the intention, what value they're approaching, right? In fact, at x equals 4, the y value is undefined, right? So this has a limit, but f of 4 is undefined. Okay, before we move on, I wanted to put a note here to remind us that for your homework, there are going to be some graphs here. Show the sketch, do a rough sketch, but make sure you draw the x and y axes nicely. You can use a calculator for the complicated functions. What I want you to do is estimate the limit by observation, right? That's it. So just estimate the limit by observation. Just look with your eyes. Please do not make a table. I don't need you to make a table. I just need you to look visually and find the limit. Okay, let's move on. One-sided limits. Sometimes we just need to look at what the function is doing from one side only, right? And so in that case, the notation that looks like this, the limit of f of x as x approaches c from the minus side, is the value a function approaches as x approaches c from the left side, right? So remember, the left side of the graph are the minuses, the right side of a graph are all pluses. So when we say c minus, it's approaching from the left. That's it, just the left of the point. So similarly, the limit of f of x as x approaches c from the positive side is the value of the function as x approaches c from the right side. So now, here's the big idea. If the limit from the right and the limit from the left both equal the same number, then I say the entire limit exists, and it's that same number. Okay, so let's do an example here. All right, let's take a look at the limit as x approaches 0 from the negative side. All right, so practically speaking, how do we do this? X equals 0 is here. If I want to take a look at the limit as x approaches 0 from the negative side, all right, imagine there is an imaginary line at x equals 0. Immediately to the left of the line, where is your graph? At what y value? 5, right? right here, 5. So I say this is 5. Okay, so now the limit as x approaches 0 plus. That means immediately to the right of that imaginary line. What is the y value of your graph? 5. Okay, now, because the limit as x approaches 0 from the negative side and the positive side are the same number, you can say that the limit as x approaches 0 of f of x is 5. Okay? Let's do another one. The limit as x approaches negative 3 from the negative side. Where is negative 3? Here. Let's do an imaginary line there. Immediately to the left of the graph, what y value does the function have? Immediately to the left of that imaginary line, the y value is 0. So as x approaches negative 3 from the minus side, that's 0. Okay. The limit as x approaches negative 3 from the positive side, immediately to the right side of this, where is your function? What's the y value? It's all the way up here, 5. Because these are not the same, I say the limit as x approaches negative 3 does not exist. DNE, does not exist. We never write out does not exist. It's always DNE. That's good enough, right? Right. So one thing I want you to be super careful about is this. One thing I want you to take note of is this. For part C, we said the limit as x approaches 0 was 5. Okay, now here's another question. This is an algebra question. What is f of 0? F of 0, it's 5. Oh, it's the same number as the limit. Coincidence. That's all it is. It's a coincidence. Sort of. Here, we found the limit as x approaches negative 3 does not exist. But what is f of negative 3? At negative 3, what's the y value? 2. Okay? So just reinforcing the fact that the actual value of the function and the value of the limit can be the same. They can be different. One can exist. The other cannot exist. They're independent of one another. All right. So the rest of this should go more quickly. All right, this is a piecewise function, and in calculus, it's important that you can draw basic piecewise functions. So here, look, I'm going to draw this one first. 2x plus 1 exists for x greater than or equal to 1. So what I do first is I plug in the 1 here to x. So the y value will be 2 times 1 plus 1, 3. So at x equals 1, y value is 3, and it's closed. And that graph is 2x plus 1, so slope of 2 over 1, that looks like that. Straight line. Okay. The upper function, this, all right, again, I plug in the 1 here, and I get 1 plus 2 is 3. Right? So I'm plugging the 1 like for the x. 1 plus 2 is 3. That's an open circle. Open on top of closed is just closed. And then what I have here is an x cubed function, right? And an x cubed function basically looks like this. Okay? All right. What do I need here? I need the limit as x approaches 1 from the negative side. Well, x equals 1 is here. From the negative side, so immediately to the left, what's the y value? Almost 3. Okay, 1 from the positive side, immediately to the right, what's the y value? Almost 3. Because these are the same, this is also 3. Okay? Yay! All right, this one's already graphed for you. Okay, we are looking for the limit as x approaches negative 2 from the minus side. Negative 2 is here. From the minus side, where is the graph? Right there. So immediately to the left, the graph is at about 3. from the plus side right here, where is the function? It's at, -4, right? The left and the right are not the same value, so I say the limit does not exist. Okay. Oh, what about here? As x approaches 3, 1, 2, 3, here we go. What's the limit as x approaches 3 from the right-hand side? So, as I approach that imaginary line, where is my y value? Where is the graph going? Down to -infinity, right? But as I approach from the other side, where is the graph now? Where is it going? Up to +infinity. Because those two are not the same, I say the limit does not exist. Okay, here. Okay. The limit as x approaches 0 from the minus side. This is x equals 0. Okay, so immediately to the right, immediately to the left of that line, where is the function at -infinity? Immediately to the right, where is the function at -infinity? Okay, so now here's the situation. Yes, these are the same. They're both -infinity. So yes, the limit as x approaches 0 is -infinity. But where is that? Do you know where that is? Nope, you don't know where that is. So whenever you write negative or positive infinity as an answer to a limit, you need to also put next to it dne, because technically infinity, we don't know where infinity is. We don't even know if the left and the right infinities are the same, right? So always put -infinity / dne. Okay? Alrighty. Okay, next one. Okay, the limit as x approaches 0, sine of 1/x. Okay, where is x equals 0? It's in that little forest of a graph. Look at the calibration here. Look at the scale. It's only going from -1 to 1, right? So look at how tiny all of this here is within, negative to positive 0.25. So a very tiny amount of space. So what's happening here? This function is coming over and then it's oscillating very, very rapidly, right? So right about x equals 0, as you approach x equals 0, do you know where in its oscillation that graph is? You have no idea. So from the left-hand side, you really have no clue. That's dne. Well, look, it's the same thing from the right-hand side. If I approach 0, I don't know where in its oscillation that is, so that's also dne. That means the limit as x approaches 0 is dne. Right? Okay, so let's recap. Let's talk about some reasons why a limit might cease to not exist, right? Okay, number 1, the limit as x approaches c does not exist if f of x approaches different values from the left and right. Okay, so for example, in which example did that happen? Well, here, B, right? Okay. Another situation is f of x increases or decreases with that bound from the left or right. Okay, where did we see that happening? Increasing with that bound? Well, here and here, right? Increasing or decreasing or both with that bound. So we saw that on C and D. A third situation where you might get dne is if you have those quick oscillations between two fixed values like we just saw in example E. Okay? All right. Last but not least, limits at infinity. Okay, this is another word for end behavior. And by end behavior, I mean what happens to the function at the end of its life, right? Towards the ends of its life. What behaviors does the function take on? Okay, several things can happen. The function might approach a value, 0, like it might flatten out at like 0, 1, -2, or it might either increase or decrease without bound. So let's take a couple of examples here. Look, here I have a function graphed 1 over x to the 4 minus 3. All right, so I want to know what is the limit as x approaches infinity. Okay, what's an infinitely large number? A million, a trillion, a gazillion, right? So as you move along the x-axis to the far rights of the positive side to positive infinity, what y value do you feel your function is going to take on? One way to do this is to literally, with your finger or with your pen, trace the function and see the behavior. Do you see how it's flattening out here at -3, y equals -3? So I say the limit here is -3. Well, what about on the opposite side as x approaches negative infinity? Again, trace what happens to this function. It's flattening out at y equals -3. Okay? Now this is different from what we were doing before. Before the two, we were approaching the same point from both sides. Now it's just the opposite. We're moving far away from each other. So one has nothing to do with the other. Okay. Here, the limit of sine of x as x approaches infinity. As x approaches infinity. Well, what is this function going to do? It's going to merely keep oscillating up and down. Well, as you approach infinity, do you know at what point this thing will stop? No, you don't even know where infinity is, for goodness sake, right? So this is dne. Okay? All right, here, this is probably one of my favorite, absolute favorite functions of all time. E to the x sine 3 pi x. So, for those of you that are interested, whenever you have an e to the x coupled with a sine or a cosine multiplied by each other, this is what happens when we have damping. So like when you have an inductor or a capacitor or some sort of energy source, right? The intensity of it might lessen over time or vice versa. This is the functions that explain that stuff. Okay, so as x approaches infinity, okay, what's this guy doing? It is oscillating like crazy, right? So oscillations we know are dne. But as x approaches negative infinity, look at what's happening. This thing is flattening out at y equals 0. So this is 0. Okay? All right. So just as if you want to start your homework, you can go ahead and start your homework. But just as an FYI, right, just in case you are at a math party one time, here's what happens. So if you have, right, f of x is equal to e to the x, right, we know exactly what e to the x looks like, don't we? E to the x looks like this. And we know what sine of x looks like. It just oscillates regularly, right? Regularly. But now when you multiply e to the x times sine of x, what happens is the sine function literally gets embedded within that e to the x function. I didn't do it symmetric on this side. I should have. Okay? It gets embedded within that. And so, that's what creates that damping effect, as we call it. All right? Super, super cool stuff. All right, I will leave you here. You can go ahead and start your homework, and I will see you guys next time.